Hello students, welcome back. In my previous part, I put some questions to you about the solubility and density of alkyl halides. So in this part, you are going to get the solutions to all those questions. So let's start then. So till now we have seen the methods of preparation, and now we are going to discuss about the properties. So first we'll discuss about the physical properties, and then we'll discuss about the chemical properties. So under physical properties we have these four. One is solubility, dipole moment, density and boiling point. So we are going to discuss about all these four physical properties. So solubility is the first one. Alkyl halides are insoluble in water, but they are soluble in organic solvents. So they are not soluble in water, they are insoluble in water. Their stability order is their stability order. So if you see, the CX bond strength decreases in the same order. So that is, if you see the CF, CCl, CF, CCl, CBr and CI. So if I move from left to right, the size of the halogen atom is getting increased. So if the size of the halogen atom is getting increased, that increases the bond length. So if bond length increases, then bond energy is going to be decreases. So this is the carbon halogen bond energy, right? So bond energy decreases, stability decreases, bond length increases. Okay, so because bond length is inversely proportional to the bond energy. So these alkyl halides, they are insoluble in water, although it has a polar nature, because they are not able to form the hydrogen bonding with water. So the second one is the dipole moment. So here I am showing a picture of methyl halide, right, CH3X. If you see, X is an halogen atom which is having more electronegativity. So there is a partial negative charge here and there is a partial positive charge over this carbon. This indicates that it is electron deficient and it is somewhat electron rich. So the dipole moment is a vector quantity pointing out from the positive charge to the negative charge. So this is the direction of the dipole moment. So the dipole moment depends on this delta as well as the bond length, right? So that is, the dipole moment is equals to, mu is equals to delta into bond length. Okay, so it is going to be depend on both the factors, on bond length as well as this delta, that is the magnitude of the partial charge. So if you see the electronegativities of the halides, so this is the order. So fluorine is having the highest electronegativity, and then chlorine, and the least one is iodine. So this delta is actually proportional to the electronegativity. So if more is electronegativity, then obviously the delta will be more. So the fluorine is going to have in case of fluorine, this delta is going to be highest, okay, and in case of iodine, this delta is going to be least. So but it is not only delta, we have to consider bond length as well. So the bond lengths are in reverse order. So here the CF bond length is least and CI bond length is more. So here, if I take the fluorine one, which is having the highest delta but least bond length, so we have to see effectively how the product is varying, because the product is the dipole moment, that is what we want. So it is not decided on the basis of only delta, that is electronegativity, not only on only the bond length. So bond length as well as the electronegativity, both you have to take into the account. So if you take both into the account, then this is going to be the dipole moment, so which is not a regular order. So CCl is having higher bond dipole moment, and CF is having lesser than chlorine, right? So here the fluorine and chlorine, both they are swapped, right? So we expect fluorine at the top of the table, but chlorine occupies the top, and the fluorine will be the next highest dipole moment. Yeah, the molecular dipoles depend upon the geometry of the molecule. This we know because it's a vector quantity. So the resultant dipole moment will be the vector sum. Okay. So this is about the dipole moment of the alkyl halides. And if you see, next is the boiling point. So if greater are the intermolecular forces, higher will be the boiling point, because more energy, more heat you need to supply in order to break the intermolecular forces. So if you go from one alkyl halide to other alkyl halide, so the dipole attractions are not significantly different for different halides. So the dipole attractions are not going to vary to the considerable extent, though they are varying, but that is only a slight difference. So, but they also have London forces or dispersion forces. So we know that if you have more surface area, the magnitude of this London force or dispersion force will be high. So the London forces are going to play the major role here, not the dipole attractions, because they don't vary from one halide to other halide considerably. So if greater is the mark, higher is the boiling point, because the boiling point is proportional to the molecular weight. So if higher is the molecular weight, then greater is the boiling point. So that's why if you take CH3F and CH3I, so it is having more molecular weight, so definitely it's going to have higher boiling point. But in case if they have same molecular weight, then the surface area has to take into account. So that is the case of isomers. So here you can say this one. In this case, if you see, both are having same molecular formula, but they have different boiling points. So their molecular weight is same, but still they have different boiling points, is only because of the difference in their surface areas. So if more is the surface area, more is going to be the interactions and more is going to be the boiling point. So this is the tertiary butyl bromide, so which is having more branches, so it is a very compact structure. That's why its surface area is less, so its boiling point is less. But here its boiling point is around 30 greater as compared to this one, because it is occupying more surface area and more is the interactions. So boiling point is proportional to molecular weight, and if molecular weight is same, then you have to take the surface area into the account. Next is the density. That's the last one. So alkyl fluorides and chlorides are less dense than water. Water is more dense than alkyl fluorides and chlorides, but whereas alkyl dichlorides, bromides and iodides are having density more than water. Okay, so for fluorides and chlorides they are less dense, but bromides and iodides they are having more density than water. So this is about the physical properties: solubility, density, as well as boiling point, dipole moment. So we'll discuss the chemical properties in our next part. While studying this chapter, if you get any doubts, you can post it for free on askIITians.com. How? First, open the website, and if you see at the top right, you will see a discussion board. So simply click on that. It will take you to the next screen. Yeah, in the next screen you will see the Ask Experts, a separate section on the right hand side. So select a relevant category for your question and simply post your question here. We experts at askIITians will provide answers to your questions within 24 to 48 hours. So students, in this part we discussed about the physical properties of alkyl halides. We started with the solubility, then we also discussed about the dipole moment and then boiling point. So now in our next part I am going to discuss about the chemical properties of alkyl halides. So keep watching.